Global AI capital expenditure is projected to surpass $1 trillion by 2030. Yet, inside the massive server farms built to train these models, a physical bottleneck is quietly stranding billions of that investment in idle computing time. The bottleneck triggers during a specific phase of large-scale AI cluster training called all-reduce. All-reduce is a synchronization operation where multiple processors must simultaneously share and average their learned weights before the next training step can begin. The root cause of this failure lies in the architecture of the internet itself. Data centers still rely on TCP/IP and BGP, routing protocols designed 40 years ago for best-effort data delivery, not the absolute precision required for modern computing. When thousands of processors execute an all-reduce operation simultaneously, these legacy protocols create instantaneous microbursts of traffic. These bursts hit the top-of-rack switches and immediately overflow their hardware memory buffers, forcing multi-million-dollar GPUs to sit frozen in I/O wait states until the congestion clears. A new architecture from Tensor Networks called the Predictive Tensor Control Plane, or PTCP, bypasses this hardware limitation. PTCP is a hardware-agnostic software overlay that mathematically eliminates microbursts by pacing traffic at the source. By reclaiming that idle time, this rack-level software optimization increases the total compute yield of the data center. Controlling this execution layer has triggered an acquisition war among global tech giants looking to secure the underlying intellectual property. Traditional internet packet delivery relies on a probabilistic model. Data is sent out, and if it encounters congestion, it slows down or resends. Exascale computing, referring to systems capable of a billion calculations per second, requires absolute mathematical determinism. This diagram compares reactive standard routing, where packets pile up, with PTCP's predictive model on the right. By executing a precise schedule at the Linux kernel layer using eBPF, packets are released perfectly spaced in constant O1 time, entirely eliminating switch queues and hardware congestion. Deployment requires overcoming a severe technical constraint. To guarantee custom code won't crash the operating system, the Linux eBPF verifier strictly prohibits floating-point operations, the mathematical calculations involving decimals that are standard in complex probability algorithms. Translating complex probability vectors into fixed-point quantization, math strictly using whole numbers, without losing accuracy is incredibly difficult. If the quantization drifts even slightly at exascale speeds, the pacing schedule fails, resulting in packet collisions across the network. Solving this mathematical constraint transforms the volatile hardware bottleneck into a frictionless software pipe. This software-defined shift destabilizes the global OEM ecosystem, which is currently divided between silicon interconnect providers like NVIDIA and AMD and traditional networking hardware vendors like Cisco and Arista. Legacy networking OEMs build their business models around absorbing network microbursts. Their profit margins rely on selling proprietary switch operating systems and massive application-specific integrated circuits, or ASICs, designed with deep physical memory buffers. If traffic is perfectly paced at the host server before it hits the wire, the network no longer needs to absorb congestion. The requirement for those expensive deep buffer top-of-rack switches evaporates. For silicon providers, this represents an enormous opportunity. NVIDIA currently dominates the AI hardware market and tightly controls the proprietary InfiniBand networking used to connect its GPUs. If NVIDIA acquires PTCP, they can embed it natively into their Bluefield data processing unit software stack. By removing the latency tax of traditional networking, the effective compute yield per GPU approaches 100%, creating a closed, deterministic compute monopoly. Competitors like AMD and Broadcom have the opposite incentive. Acquiring PTCP allows them to offer a hardware-agnostic software fabric that makes standard Ethernet outperform NVIDIA's proprietary InfiniBand, attacking their rival's main competitive moat. For traditional networking vendors, buying Tensor Networks is a defensive act of self-cannibalization. For the silicon providers, it is an offensive weapon designed to secure absolute dominance over AI compute infrastructure. The implications extend to a global scale. The major hyperscalers, Google, Amazon, Microsoft, and Apple, invest billions in private submarine optical cables to connect their global infrastructure. By applying PTCP's predictive traffic federation across these massive wide area networks, a hyperscaler could safely run its global optical backbone at 85 to 90% utilization. That is nearly double the standard industry rate of 45%. Simultaneously, these companies are building custom AI silicon. Chips like Google's TPU, Microsoft's Maya, and Amazon's Trainium are designed specifically to escape reliance on third-party hardware vendors. Acquiring a hardware-agnostic control plane removes the need for an external vendor's proprietary networking. This allows hyperscalers to perfectly synchronize their custom silicon clusters on their own terms. This chart models total cost of ownership savings across a global data center footprint. If PTCP reclaims just 10% of compute time stranded during distributed training, that optimization generates $100 billion in reclaimed compute yield by 2041. There is also an operational bonus. Because PTCP operates at the host kernel layer, it can identify and drop volumetric DDoS attacks and BGP hijacks before they traverse the network. This allows a hyperscaler to scrap billions of dollars in legacy security and scrubbing hardware. Hyperscalers own the custom silicon, the custom server architectures, and the global optical networks. They are uniquely positioned to capture every dimension of PTCP's theoretical value entirely in-house. This curve tracks Tensor Networks' strategic valuation. An early acquisition prior to 2028 costs in the low billions, despite high integration risks. Waiting for universal adoption pushes the valuation past $30 billion, making it too expensive for anyone but the largest hyperscalers. To secure a 10-year economic moat, Microsoft or Google must execute a near-term acquisition before the intellectual property becomes a vendor-agnostic standard. The dark horse remains NVIDIA. Securing this software layer transitions them from a hardware manufacturer into the sole architect of a turnkey, deterministic AI supercomputer. Whoever attempts this acquisition will face severe regulatory friction. Global bodies like the FTC and the EU Commission will fiercely scrutinize any entity attempting to consolidate the foundational protocols of the next-generation Internet. To satisfy antitrust demands, the acquiring entity will likely be forced to open source the core data plane agents running in the kernel, while solely monetizing the proprietary global orchestrators that manage the network. The Predictive Tensor Control Plane transitions the Internet into a deterministic system. The entity that acquires and scales this architecture secures control over the physical economics of the digital economy for the next 2 decades.